Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is ET 122, Digital 2. Today we're going to have a discussion about edge detection. So a couple lectures ago, I discussed about clocks. There being 4 different types of clocks. And if we remember right, just our regular clock signal, it's down, up, down. We could detect a pulse. We could have it take the beat here at the high portion of it. Would take the beat here, take the clock, excuse me, at the low portion of it. We could take it at the rising edge, and we could take it at the falling edge. Okay, now the whole point of a clock, remember, is to be a beat. So the question in your mind should be, when does the beat occur? Well, here it's pretty obvious. It's right there. Right there, it's exactly when the falling edge happens. Ideally, again, and realistically, there is going to be some transition time, but realistically, that's a really tiny time period compared to this time period that it's in a high zone here. So the question is, where is the clock occurring, excuse me, at the high and low regions? So where is it? That's the problem with it, okay? So what we want to find out is the edge detection. So basically, normally clocks use positive or negative edge detection. These are not as useful. So very rarely are you going to see a clock with just a positive high, the negative low. You're normally going to see positive rising or negative falling edge clocks. So how do you do it? That's your first question for anything as a technician. How are you doing this? Okay, so remember way back our Boolean algebra. Okay, so Boolean algebra, let's say C and not C. Remember that law? It's always equal to 0. So just think about that. When C is 1, not C is going to be 0, so it's always going to be 0. When C is 0, not C is going to be 1, so that's going to be 0. So that makes sense according to Boolean algebra. But I'm going to tell you, not always. So, and here's C coming in. Here's not C coming in, because right there is not C. So according to our traditional Boolean algebra laws, we should always get a 0 here. And I just told you that's not true, because what if this guy has a delay? Okay, so according to a timing diagram, where let's say C is going along this way, and that's C, and then this guy's not C. So remember, it's going to be opposite, an inverter. But now let's say there's a slight delay by that much for it to transition. So C and not C, what are you going to get here? There's a brief moment in time where they're both high. So you're going to get a positive high right there for that brief moment of time. And what you've just discovered is the positive rising edge of C. Okay? Not too hard. They're occurring exactly at the rising edge. Okay, you want to detect a falling edge? Just invert the signal. And here we go. Here's a good setup for a negative edge detection device. So here we've got signal C coming in, and it's going to hit an inverter straight off. So let's say C is going along, and it's doing this. It's down, up, going like that. Now it's going to be not C. Yes, there's going to be a delay. Ever so, whoop, I got to remember it's an inverter. So it's a slight delay from this guy. Remember, there's a region of delay right there, right there. Okay, so, but that doesn't really concern us because both signals have gone through that. What that matters here is not C is being fed in here and it's being fed in here. It's a differential delay, and I'm going to call this C prime here. It's the differential delay that makes up these brief moments of time. Okay, so now C prime is going to be the inversion of not C, and it's going to have a delay. From not C. So here's a region of delay, delay, slightly delayed right there, okay? But now what we're doing is we are ANDing this guy and this guy together. So let's figure out when we get simultaneously high. Well, nowhere here. All of a sudden we find this spot and this spot where they're both briefly high for a time. And then according to this graphic, I don't think we have any other times where we're both briefly high. And what we found here, because we didn't continue beyond. Had we wanted to, we could continue beyond here. But basically for the portion we did the analysis of the timing diagram, what we found is, boom, right here, that negative falling edge perfectly coincides with a pulse on our negative edge detector. Pretty cool, huh? Not too hard. Well, all you have to do is just to account for the fact that that is a delay. And how is it really done? Some of these devices are very, very, very fast, and that delay may be in the order of microseconds. What you could do, think about this. Invert it again, invert it again. You want more delay? Invert it again, invert it again. As long as it's an odd number of inversions, you're gonna get an inversion. So here's 1 microsecond delay, 1 microsecond, on and on and on. You got 5 microseconds of delay. There you go. That's how you get that 5 microseconds of delay, and you get your nice pulse detection. You're basically your negative edge. And this is called a buffer arrangement. And this is an inverting buffer because there's an odd number of inverters. If there was an even number of inverters, it would be just, excuse me, an inverting buffer has an odd number of inverters. A buffer has even number of inverters because you invert something and invert it again, you're back to what you started with. A buffer, the whole purpose of a buffer is to delay something, okay? So let's apply a positive edge detector to something like our gate enabled, our gated SR latch. Okay, so this is our regular gated SR latch. So now what we're going to do is we're going to apply our positive edge detector to the enable, and we're going to call this signal the clock. Okay, anytime the clock is going like this, according to what we just discussed upstairs, anytime we get a positive edge here, we get a brief pulse on enable. Okay, so when that positive spike occurs, it briefly enables the gated SR latch to 1 set given S1 R0, 2 reset given S0 R1, 3 stay latched wherever it was previously given 0 and 0, depending on your previous state. If you were set, you're going to stay set. If you were reset, you're going to stay reset. And it's also going to give you an opportunity to drive off the cliff. So the unknown zone. where you're trying to simultaneously set and reset. Okay, so you still have the opportunity to crash, but your chances are much smaller of doing so because that's a brief moment of time, that's a brief moment of time, that's a brief moment of time. Hopefully it does not coincide when you're trying to simultaneously set and reset at the same time. Okay, chances are just smaller of doing so. Like they said in airborne school, it's a big sky, but they're small bullets. Did not really ease my tension though. Okay, so now that we've had a discussion about edge detection, what happens if you apply an edge detection device to a D-latch and compare it to an active high enable D-latch? So let's compare and contrast, if you will, the 7475, which is an active high enable quad, meaning there's 4 of them, D-latch on the same chip. And remember, a normal D-latch, there's our D in, here's our enable. And notice that there's no special symbols on that thing. And here's our Q. Now we have a 7474. And what this is a positive edge detection. Oops, I spelled that wrong. Detection. Positive edge detection, dual flip-flop, meaning that there's 2 of them. Flip-flop versus a latch. So what's that one look like? It's got a D coming into it, and it's got an edge detection. There's no bubble because it's positive, and that's giving the signal clock, and here's Q. Okay, so that's what we've been working with previously. This is what we just discussed, and now we're going to compare and contrast what happens to these guys given the same D and the same enable and clock. Okay, so let's do this one for the, say this is our active high, and here's our, let's do that in red. Here's our positive edge. Okay, they're getting the same enable and clock system. The first thing you need to do is just divvy up when's its positive edge. There's a positive edge, there's a positive edge. When is it active high? Right here, right here. Okay, so let's do for the first one, when it's an active high enable D-latch. Okay, so active high means it's taking, and let's assume the latch is initially in the reset condition. So it's going to be reset until it's enabled in this region here, and it's going to follow D when it's enabled. And D goes high, and then goes low when it's enabled. When it's disabled, because remember this period right here is the disabled, it's just going to stay latched where it was. Now again, it's enabled, and it's still reset condition. D is still in the reset zone. So it's going to stay reset until D goes high. It's following D when it's enabled. Okay? So that was for our regular, that guy. Now let's go over to our positive edge detection, D flip-flop, which is different than our active high D latch. Okay, so now it's going to take at the positive edge. Again, we're not changing enable, and we're not changing the data stream D. Let's see what it stores. Again, assuming it's reset. Assuming it's reset, it's going on until the positive edge occurs right here. It samples it there, and that's a 1. And it's going to stay set until the next positive edge occurs, which is right here, and it's going to sample D, and that's low. And it goes back down. Okay, see how they behave? Totally different. Positive edge detection versus active high enables. So that's a pretty cool example how edge detection can change from one device to the next. One last super quick discussion. What's inside a D flip-flop? Well, what's inside a D flip-flop, obviously, a positive edge detection device, and there's, remember, a regular, here, so that's definitely the clock, and that's feeding the enable of an SR latch. I'm debating if I want to do all of this. Oops, not S. You guys know what SR latches is, but and what the D is it's being fed straight into S, but it's being inverted to R. And I know I just said in those positive edge detection devices, look for that differential delay. It doesn't, this one, ignore that. Basically what you're getting a situation is, have I gone over? Yes, I've gone over buffers. This one is extremely buffered. This one is not super fast. So basically S and R are always opposites. So what you see here is basically you were using an SR latch with a gated SR latch with S and R inverted. So you're never getting a simultaneous high trying to simultaneously set and reset it. If it was buffered, yeah, you would get that briefly, momentarily, it would screw everything up. And then finally, you also have a positive edge detection device. What this is showing you inside a D flip-flop, you've got a basic gated SR latch. And this is critical because an SR latch is a basic building block for any of the other devices that we're going to be using, as we just showed inside a D flip-flop. And as we're going to see in the next lecture, the JK flip-flop.